Reminder about that. We did the worksheet the other day. The worksheet goes up on Blackboard. The answers go up on Blackboard as well. I scan. It was quite a busy worksheet. There's a lot of small details, all right, to put it all together. So have a look at it. There were word problems, maximising and minimising as well.
That's coming down now.
Thank God, I'm glad. And then I'll have to say, why couldn't these people solve my problem, okay? She's just going to get to me. Oh, what does he do? Anyway, we'll get started, all right, because I know he'll just push one thing as usual. I love how he's told you he's coming, all right? Thanks for that. So it says integration is the process of finding the area under a curve. So have a look at these pretty pictures, all right? You know how to draw these gorgeous curves because you're so good at 124 mathematics. Remember, there are times when I ask you to sketch things from our past. Oh, Dave. Look, everybody watch what he does, okay? Everybody, what is it about
Bring it down here.
Oh, bring what down
here?
No,
you look.
Yeah.
Now,
and then
look at the pen.
And look at the pen. Oh,
and press it with the pen.
I'll press it with
or the pen or the mouse.
But no, I think because it's going.
Okay, pen.
And we did
red. Okay, go back here and go Control P.
All right, go Control P. Everybody watching? Control P.
Yeah. Whoop.
I'll get my real pen and start writing on it. It's again, you know how last time you said to me I was in some other icon?
Yeah.
But what am I in that is strange? What's the thing? Because it looks like it's
why
the
is
same
it not?
note.
Is it even acknowledging you?
It's probably not in. It's not in.
No, we need out again.
We need to get out.
And show.
I love how you. Yeah. Okay. Get that out.
Keep what annotations?
No, we haven't. Yeah. What? Oh, might have been an old one.
Oh yeah.
That's
could
my
well
number
have been.
3. There it is. Open her up.
All right.
Okay. What am I
doing? Get done to it.
Get done to it.
Now that.
Welcome back.
Now to that mode.
Now that mode. Is it in tablets? What have I hit?
Okay, yeah, pen. But is this actually... It doesn't seem to be acknowledging anything.
But it was this morning. I played with it.
It was?
Yeah.
Okay.
Highly technical work here.
Take the battery out, put it back in again.
Well, they did suggest I turn it off and on.
Yeah, exactly.
I knew you'd be faster. Oh.
Okay. And now to full screen.
Yeah.
I assume. Oh, that's the mute. And then how do you normally go to full screen?
I go that one up there, and I say the bottom one.
All right. We're all happy.
Thanks, Dave. That's more chocolate I owe him. Gosh. All right, let's see. Does it still work now that he's left me? All right. Okay, here we go. I was reminding you about these pretty pictures that you draw, okay? Because even in the worksheet, as could be in the quiz, you might get asked to draw a simple curve from 1 to 4 because at some point, all right, you want to remember your 1 to 4 maths. So please make sure you go and practice those sort of basics. So we're figuring out the area between that curve f of x and the x-axis is written as. See how it says area equals absolute value? The absolute value comes in because you're talking about if the area is above or below the x-axis. And the second one says the area between the curve and the y-axis is written as. You'll notice what's different is it says f of y dy. Now we're coming back to this idea. We're still building up to this area idea, but that's where we're heading. All right, we are heading to those. And it says, why do we care about the area under this curve? Well, I'll just quickly go through that because we're trying to catch up a little bit there. It's just going to help you figure out the area under these curves. Remember, you can do areas of ordinary shapes like triangles, circles, rectangles, trapeziums, but once the curve has got these curves to it, all right, our formulas fall away. We don't have a formula for every single shape, and that's where our integration is going to come up. So, round 1, even if you did this at school, you probably didn't discuss these Riemann sums, okay? You may or may not have discussed these Riemann sums. So this is new to most people, all right? And it's going to be questioned in the worksheet. It's going to be questioned in the quizzes. So please make sure you get your head wrapped around this. We're going to do a few examples together. But it's a first way of dealing with integration. So it says, one method of determining the area between a curve and the x-axis and between two values, x equals a and x equals b, is by constructing rectangles under the curve. The height of that rectangle shown is based on the left edge of the rectangle. So first time round, what you're discovering is this is going to be a rectangle, and the height of this rectangle, if this is the value a, then the height is going to be f of a. Now you know your function notation, all right, so you should know what f of a means. Whatever the function is, I'm going to put a into it, and that'll give me the height of that particular rectangle, all right. So it says, oh, you're joking, it didn't, did it? That's all right, just checking. So this here, f of a, is going to give us the height of our rectangle. So first time round, it says a better approximation is found by dividing that interval. So we had the a and we had the b, but if we took just one rectangle, it really wouldn't be a great approximation. So a better way is to break it up into smaller rectangles, and that's what your job's going to be. Your job is going to be to consider one rectangle, then two rectangles, then maybe 5 rectangles, and maybe 10 rectangles, and your job's going to see how the approximation keeps getting better and better and better. It's getting closer to what the real area is. So this idea of breaking it into a number of equal subintervals and constructing a rectangle in each subinterval. So again, you're going to break this up. It's going to vary each time. So for 4 equal subintervals, it shows you it's done the 4, and what it's decided then to do is it has to give you this change in x. That's what that little delta x, that little triangle x means, and it wants to figure out what this, and this. The number is exactly the same. It has to be exactly the same so that the rectangles have the same width, if you want to call it that. When you go to do their height, each of those rectangles has a different height. So what ends up happening is on the first one, this is the height, so it's f of a multiplied by delta x. So there's your first rectangle there. When you go to do your second rectangle, you need this height here. So it says f of, and then it says whatever a was plus this little extra bit, and then you multiplied it by delta x. So there is your second rectangle. And you go along to your third rectangle, so it figures this out, and then it follows through with the fourth one up here. So you've now got 4 rectangles, all right, being summed together. Another way to show that is they've taken out the delta x, put it down here as a common factor, and these are going to be the f of each of these numbers. This one, this one, this one, and this one. So you notice there are 4 there. So f of, depending on what the function is, so we're going to wait to here, but this is just still in general form. It comes through for a formula for you to follow. It says every time we do this, you get told how many rectangles to break it into, so that's going to be how many equal subintervals. The next job we'll do is figure out delta x in every single one, and then the formula says exactly what went through. Depending on how many rectangles you're going to have, it's going to be denoted by, all right, this sum of, so this is a big sigma. If you haven't seen it before, this is a big sigma sign. It's a Greek letter. So sigma is the sum of, and it wants you just to add up all those areas of those rectangles. That's what it's doing in words, but in notation it looks pretty hard. It is not as bad as it seems. So that's just the general formula. It then goes on to say we're going to have to consider the left-hand side, and then we're going to consider the right-hand side. So you can see on page 30 it says left Riemann Sums, and then halfway down it says right Riemann Sums. So the first time round, see the SL coming up here? This is how we're going to denote that we're working on the left-hand side. And what it's going to do is it basically takes it, and these rectangles that have been formed, it takes the left-hand sides and it goes through and figures them out. So we're going to put this into practice. Again, it looks a lot harder when you see it like this, but it will be a lot easier once we put numbers into it. All right, so the left-hand side's going to get done like that. When it then goes on to the right-hand side, what happens is we're going to fill out a table. Both of these are going to need little tables, so that's what makes this so easy. And I'll show you the shortcut when we get to the real examples. You notice that these two here, you don't really need to, look, you could, when you go to write this down on your resource sheet, you're most welcome to write this down, but this looks very formal. What you'd rather do is probably put down an example with how you're going to use it with the left-hand side, how you're going to use it with the right-hand side. You will notice that there's a difference, so you'll see here and here, and you'll see here and here. But once we put it into action, there'll be a much easier way for you to remember this little setup, okay? So here's the first one. Now this one is done or not done? Done on page 31, I think. It's the same thing as what's on the top of page 31. So I'll just go through each of our steps. Here comes the question. Form two rectangles to form an approximation. 4. Now this symbol, this integral sign like this, means the sum of. All right, that's actually a shorthand symbol that they came up with a long time ago. So we say the integral from 0 to 1 of x squared. Now what you are actually about to do, if you know what an x squared diagram looks like, it's a parabola. We're going from x equals 0 to x equals 1. We actually are looking for this area under that curve. So if you draw that up there, keep in mind that this is what you're actually doing each time, and it should give you an idea of, yeah, oh, I can see what I'm trying to do, and I can see why I need this integration method, because I can't do it any other way because of the curve of the parabola. So it says the first time, two rectangles. So the first thing I'll get you to do is put n equals 2. So you get into a pattern. First thing is always notice how many rectangles you're going to break it into. So this is, sorry, at the bottom of page 30. And it says two rectangles, and then the next thing I would do is do this delta x. Now delta x gets defined as b minus a over n. And in this case, the bigger number was 1, the smaller number was 0, as you can see from the top here and the bottom here. And the 2 is there because that's the n from our rectangles. So I would start thinking, look at how many rectangles, that's going to give me my n equals. Look at the numbers on the integral sign because that's your b minus your a. So this is going to give us a delta x of a half. Now what would happen then is we'd go to a table. Now the 0 at the bottom starts, the 1 at the top has to be the very last one. And you can see 3 boxes waiting for us as such. Now keep in mind, it said two rectangles, and that 2 led us to the delta x being a half. This is the secret here, because the jump has to be a half, and it should get you to the top number. So in this case, the missing number is 0.5. You can write it as a decimal, you can write it as a fraction. So first round, how do you find the values that are going to go in there? This is just add a delta x and then add another delta x. But you should remember the very first number 0 comes from the bottom, and the top number, right, sits there. So you can put your 0 and your 1. Maybe you're not sure how many boxes to leave. So then say, well, if I start at 0 and jump by a half and jump by a half, I will get there in 3 boxes. Now down the bottom, this is another thing that people find hard. But once you get practicing, what you want to do is find the number of rectangles, find delta x, and from this particular integration right there, f of x is whatever that function is. So right now, f of x is x squared. So you want to highlight that. When someone says fill in these boxes and follow the f of x, you'll say, where is my f of x? It is in the integral sign. So it's the integral of f of x. It will be sitting there, right there. It can be an x squared, it can be a 1 on x, it can be a 2 to the power of x. It can be anything at all as long as it's a function of x. So now to fill in the boxes on the bottom, what do? This one here is just 0 squared. This one here is 1/2 being squared. So the numbers are 0, then a half squared, which is a quarter, and then 1 squared. Now you'll notice it didn't want 1 squared, because when you're doing a left Riemann sum, your boxes will not need the right-hand side. The very last one will not be needed. So there was a really complicated formula there before. Or when you draw these boxes, say to yourself, highlight it, add it to your notes now. When you're doing a left Riemann Sums, the right-hand box down here has nothing in it. Not a zero, just a dash. You do not need that value. And you'll see the opposite happen when we do the right Riemann Sums. Having a bad day. All right? Oh, that's going to go down. I might even have to edit that one. So, shocker before Dave gets to it. So this is the formal proof down here. Again, that particular formula looks a lot more complicated than what it is. What I want you to do is just remind yourself, S of L will be approximately, how you draw that, the two squiggles mean approximately, or you can do an equals with a dot on top and dot on the bottom. And then what you're going to do is add up all the numbers that you have, and I'm going to put a tick, and then a cross, so that you remember. Because you're doing the left sums, you are only going to need these two and not the last one. So what should appear here should be 0 plus 0.25. So whatever goes in the bottom of that row there, 0 plus 0.25, not the last one, and then you're multiplying it by delta x, which in this case was a half or 0.5. So you can see that it's going to come up with that, all right? It's in your book, and there's our answer. Now that's an approximation because they've taken the rectangles using the left-hand side of the rectangles. So then what happens is, if you do the same question, but you use the right-hand side, so this time, start it again. First of all, I'll remind you, if you keep into a good pattern from the beginning, n equals 2. So the very next thing I do is figure out my delta x. It hasn't changed, but I'll go through the 1 take away 0 over 2. So again, it's a half. Get your boxes ready. There's your lower limit, there's your upper limit, and the middle guy has to be a half. Your f of x is still the same, so your f of x is still x squared. So you're going to need 3 numbers. You think you need 3, but because you're doing the right-hand side, you notice you'll put a cross or a dash in the left-hand box. So it's only ever 1 that gets missed. Okay, it's only ever 1 that gets missed. How'd they get these answers? This is a half being squared, and this is a 1 being squared. So obviously those numbers there. This formula again looks complicated. What you want to get used to doing is saying it's approximately equal to. You don't need the first answer, but you need 0.25 plus 1 multiplied by the delta x, which in this case is again a half. Now you're going to get yourself another answer. You can see 2 answers, 0.125 and you can see 0.625. Now there's quite a variation in those 2 areas. So this was like a first time round. Someone said we need to find the area under that curve. What's the best we can do? And they came up with this method. And you can see it varies from the left-hand side answer to the right-hand side answer. Now, there's an exact answer, which is where we're leading to in this lecture today. But for the moment, you understand that this was how they first of all did it before they got their integration rules. And this wasn't such a bad idea. They realised that the more rectangles you take, the better your approximation gets. So the more rectangles, the better your approximation. So you can see that up on the next one, it's got form 4 rectangles to find an approximation for exactly the same area, from 0 to 1 under x squared. Here we go again. This says n equals 4. When you go to find your delta x, the first thing you do is take the first number 1 minus 0, but this time you're dividing it by 4, so delta x is going to be a quarter. That means when you go to draw your table up, your table now has more boxes in it. It's got to start at 0 as usual. It's got to end at 1, and if you're not sure about what those other numbers are, you're adding a quarter, you're adding a quarter, you're adding a quarter. So hopefully you're okay with a quarter plus a quarter is a half, and then another quarter is 3/4. So they get those 3, and then how do they get their f of x values? Their f of x values come about because they follow the f of x, which in this case is x squared, and because we're doing a left sum, okay, we don't need this guy here. Now you'll see there's more numbers to add. So when we go to do the sum, remember, it looks complicated. You don't have to write that, but you can if you want to, if you're a follower of it. What you are saying is you will need this, 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 and not this one down here. So you will need to put those 4 in a bracket, multiplied by a quarter, and it gives us a better approximation. So this is getting closer because this time I put 4 rectangles together. I'm going to do the right-hand side. Again, we'll go through it quickly because now you're getting the idea of set up how many you've got in your table, find the values. Because this is a right sum that you are doing, you want to cross out the first guy and you will need 1, 2, 3, 4 values. Put it together, and again, the 2 values are still not the same, but they're getting closer. So have a look at the 2 values. 0.21875 compared to 0.46875. So they're getting closer. So this is the idea. When you do the worksheet, when you do the tutorial, we might ask you to do the same one with 1 rectangle, 2 rectangles, 5 rectangles, 10 rectangles, and we want you to get the idea that you're getting better as you get more. Now this one is the one that is at the bottom of page 31, so it is not filled in. So my suggestion is grab a ruler out if you can. Yeah, Cara? Okay, here we go. On this one here, this is the one at the bottom of page 31. It looks like the same question. It's the integral from 0 to 1 of the area under the x squared curve. dx just means with respect to the variable x. Now, first time round, we need left. We're doing 5 rectangles. So the first thing I'd do is near the 5, I'd put n equals 5 up the top, or somewhere near where it's the rectangle information. I would then at some point do my delta x. Now, Cara, here comes that bit you wanted, which is you want the b minus the a over the n. So this one, okay, it's the bigger number minus the smaller number over however many rectangles we're getting. Okay? So b minus a, so the 1 minus the 0 in this case, divided by 5 because that was our new n, and that's obviously going to give us a 1/5. Now you can write that as a 1/5 or 0.2, whichever one you would prefer. Are you ready for the table? Because your job is now to draw that table up. You will need a table, so I'll just go with a quick line like this. This is x, it starts at 0. You have to end it at 1. You have to take jumps of a 1/5. You can either write it as a fraction or you can write it as a decimal. All right, which one would we prefer? Will we stay with the decimals? Here we go. Jump that 1/5, so I'll put jumping 1/5. I will put 0.2 for that guy. Jump another 1/5, you'll get 0.4. Jump another 1/5, 0.6. Jump another 1/5, and then jump another 1/5. You should have finished by that stage. So you notice that you keep adding on a 1/5 as you go over, and you get to the last number. Now, because this is a left, which one don't I need? Sounds a bit odd, but which one don't I need? The right guy. So over here, put a cross at the moment. Your f of x in this case, all right? F of x is always what is sitting there, so I'll put it on this side. F of x is equal to x squared. All right? Put in the numbers. Now, on your calculator, that's all you need to do. Again, I'm trying to get you to, in some manner, be efficient when you get to your quizzes. We're finding people taking too long. So get your calculator ready. 0 squared and put the answer. 0.2 squared. Now, I'll write down what I'm doing, and then you figure it out. So fill in the table for me. So this is what you're going to be pushing in on your calculator. What are the numbers that we need as we go along there? So 0 was the first one, 0 squared. Then comes in 0.04. Then comes in 0.16. So just check on me. You can write them as fractions if you want. 0.36. This should be a 0.64. Are we all okay with those numbers? Now, you've got the table filled out. And remember, in a quiz, you have to be efficient. So figure out, and you notice I've already put the cross at the end so I don't mix this up. Because this was a left sum, okay, because this was a left sum, it said I would need the answer 0 plus 0.04 plus 0.16 plus 0.36 plus 0.64, end of the bracket. So there should have been 1, 2, 3, 4, 5 values that I put in, multiplied by my delta x, how you want to write it, as a fraction or a decimal, and then I need the answer to that. So tap away. 0 point. Try again. I'm getting something different. Anyone else? Type it in for us. 0.24. That was the same as Rebecca. Then I must have typed it in. That's confirmation with Rebecca. Yeah? 0.24. All right. 0.24. Rebecca, apologies. You were right. 0.24. Now that was the left-hand side. Okay? So your job is to do this again for the right-hand side. So you need another table written underneath it. All right, another table written underneath it. So I'm going to do my table down here pretty small. I've got my x, there's my 0. I'm jumping with the same numbers, 0.4. Now I know you're going to say, could I just use the other table? All right, you know that the values are the same, you know all the numbers are the same. What changes when you go to do the right sums? What changes? You don't include this guy here, so everything else stays the same. So you can use the same set of values. Obviously they are the same set of values. There's just one new guy, 1 squared, which is 1. So I'm going to write my right sums over, see if it goes down, it won't go down the bottom. So I'll put my right sum and I'll be adding up my 0.04 plus 0.16 plus 0.36, I'm going to come around here, 0.64 plus 1 multiplied by my 0.2. All right, I need an answer on that one. 0.44? Anyone else confirming? Yep. 0.44. So you can see the left sum and the right sum, okay, not the same, so don't sort of think they're meant to be. They're just, remember, approximations. One was using the left-hand side of the rectangles, one was using the right-hand side of the rectangles. So you've gone through it once and you've said, right, I realise the table's important, I realise that my n is important, my delta x is important because that helps me set the table up. I may only need to write the table once if you're going to be efficient in a quiz. Keep in mind which ones you want to use on a left and which ones you want to use on a right. Okay? So, harder one coming up. I think we turn the page over. We've got a bit of space for this one as well. Now you want to be efficient, remember? You want to be efficient. So when you go to read this, it says use 5 rectangles. So the very first thing I do is n equals 5. It says go and do a left, all right, a left sum to find an approximation from 0 to 5 of this particular function. So if you want to, circle that and say f of x in this particular case is 1 over the square root of 1 plus x squared. Put it in really big writing because that's what you need to implement in the table. So once you find all the x values, you're going to have to come back and put them into that one there. Not as bad as it seems because I'll show you a nice efficient way to do this. All right? So we've got our n. The very next thing we do is find our delta x. So here we go again, Cara. Our b minus our a is always our bigger number. Take away our smaller number over the n. So 5 minus 0 all over 5 turns out to give me a 1. So what does that mean? I'm going to set my table up and my jumps are going to go up, my intervals go up by 1. So here's the thing. I only need the left, so I'll get this ready. Here's the x. It starts at 0. Jumping by delta x, so that's 1. Jump again, 2, 3, 4, and the last one is a 5. Which one don't I need? Because that's sort of what I do straight away. I'll lock that guy out. Because it's a left, we don't want this guy down the end on the right-hand side. Something that makes you think which one has to be thrown out. Now go find the values. Now you're putting the 0 in. Now keep it in third form, because if you go to the calculator, you're going to get decimals every single time. You are better off, more efficient for you and more correct, to actually put the thirds in this table. So put the 0 into this position and you're going to get 1 on the square root of 1 plus 0 squared. What's that otherwise known as? 1. Then you'll go and put 1 on the square root of 1 plus 1 squared. What's that otherwise known as? 1 on the square root of 2. Much easier than the decimal that actually is. When you go to put the next one in, 1 on the square root of 1 plus 2 squared. Keep going, guys. Do them all for me. Tell me what they all are. So there's a 1 on root 2. Next one is 1 on root 5. Make sure you can figure them out. The next one is 1 on root 10. Just confirm it so we're both agreeing. Not having a good day, remember. 1 on the square root of, what's the last one? 17. Now, you are still better off putting that in, because when you go to add all these numbers up, at least they're in third form, and you're not going to have to tap in lots of decimal values. So, we wanted the left-hand sum, so the left-hand sum is approximately equal to 1 plus 1 on root 2 plus 1 on root 5 plus 1 on root 10 plus 1 on the root of 17, not counting the last one, times by delta x, and delta x in this case was a 1. So if you label everything, it's all sitting there nicely, delta x up the top. All right, I can see it sitting there, and that's the number that always goes there. Hit the calculators, because this time it is going to give you a decimal approximation. That'll keep going, so I'm going to ask for what this is, and then I'll go to 2 decimal places, because it needs to be rounded off. What sort of value did you get? 0 point? No, not 0 point, 2 point. 2.71. We're agreeing, Cara, so you and I are agreeing. Anyone else with us? 2.71. So your answer should come out to be approximately 2.71, and again, be efficient with your calculator, because if you had put all these in as decimals, you would have been punching in a lot more decimals, because what you don't want to do is round off each of these guys and then have another answer rounded off. You are rounding off too many times, so you want to put these numbers in and then round off just once at the end. Okay? Just once at the end. Alright, so do you think you're left and you're right? You figured out what to do? The system is find what n is, find delta x, put it in your working every single time, figure out if it's a left or a right, do the table, cross one of the last guys off, either the right-hand side or the left-hand side. And in the tutorial, as in the worksheet, we might get you to do the same question on the left, and we'll do the same question on the right, and you can just compare the two answers. Now that to most people is new, because nobody really probably delved into that when they were at school. Okay, you may have had a teacher who brought it up, but most people don't ever come across that. Now we're coming to the part that most people did at school. So here come all those words that you're used to. We'll get it started. We'll probably take our break a bit early. It says primitive functions, otherwise known as indefinite integrals. Okay, so why do they use those words? So it says, when we know f dash, keep in mind that is not a mistake, it's an f dash, and it means the derivative. When we know the derivative, f dash, we can anti-differentiate. Anti meaning go backwards, okay, to find the original function f of x. So hear that again. This is said in words, all right? You are starting with the derivative, and you're going to put into place something that brings back the original function f of x. Now this is why I got you to really pay attention to your labelling. when you were doing this last week and when you would do it for us this week in the quizzes, your job will be have an f of x, the next one labelled is f dash of x, the next one labelled is f double dash of x. Make sure you label because they're all vital to your calculations. This is us saying we're going backwards. We're going to hand you f dash, a derivative, and we need you to tell us what the original could have been. And it says it's called the primitive for an obvious reason. It means the original. So it said, when y equals x of n, x to the n, this is what we did as of last week. We differentiated it. And we put the n down. So this is just pointing it out. It's spelling it out for you. First of all, the n goes down. It says multiply by the power, so the n drops. And the second thing you put into play is reducing the power by 1. So there are the two steps that we've been taking to find a derivative. Now it says go backwards, all right? So we have to undo. So it's going to start on the right-hand side. It'll start you will start with a function written as an x to the power of n. It must be written as this. This is going to be one of our problems, if we know our indices or not. X to the n. Going backwards, if we had reduced the power by 1, then we're going to do the reverse, which is increase the power by 1. So you see this has gone up by 1. And if we had multiplied by the power, we're going to do the opposite, which is divide by the power. So when you get your original function, this is what your original function is. Now, keep in mind, this is what it starts as, this is what it's going to start as, and this is what you go back to. So this was the derivative, and this is you saying this is now the original function that I started with. All right, so there are the two steps that you're going to need. They're very simple steps, but they're going to really throw a lot of people because they can't remember, and I mean this sincerely, the add 1 to a number is going to be the worst enemy, okay? Because I'll say, did you add 1? And you'll hit yourself because you'll keep saying, I keep forgetting to add 1. And you'll find the simplest questions are going to just knock you out, and you'll go, I can't believe I can't add 1. It does say, note, however, that whenever we anti-differentiate, we need to add this guy, a plus c. It represents a constant. A constant is any number, any positive, any negative, any number that does not have an x next to it. It's a constant. So it can be a value, and it represents that constant that may have existed when the original function was differentiated. So have a look at this little example. If we'd started with x squared plus 5x plus 6, when you find the derivative of that, when you differentiate it, you get the 2x plus the 5. Most people can see that. And the constant's derivative was 0. So the constant's derivative was 0. What happens when we go backwards? That means if you start with 2x plus 5, following these rules we're about to put into play, you're going to get an x squared plus a 5x, but this guy here is something that is unknown to us because it could have been a plus 6, could have been a minus 6, could have been a 1 on 6. That's what the plus c represents. It's some sort of constant which to this point doesn't need to be known, but later on gets found out as we use this a bit more. So the idea is that now you've got this plus c, and those plus c's will also hurt you in quizzes if you don't remember them. Okay, we have been known to give you big hints when it comes to that quiz because you don't want to forget your plus c because it's part of the answers every single time. So it says down the bottom of page 32, so if you start with your derivative, could you please make sure you understand dy dx is either going to be f dash, is going to be where you start from. It must be in the form x to the n. So this is crucial again that you know your index laws. So your indices are going to hurt you if you're not prepared. And to go back, you'll notice that this is what the derivative was, and this says your original function, you can call it y, or you can call your original function f of x. So what did the words say? The power goes up by 1, and you divide by that power. So it's going to go up by 1, and whatever the number is you write there, you will also write it underneath that particular term, and you're not going to forget your plus C. So put a big highlighter on that plus C. So first round, we're going to see how much you remember your indices. So you'll be amazed. You are not doing a derivative, so get your mind and lock it out of the derivative zone, and now you're thinking going backwards. What I'm going to put, it's down the bottom on page 32, I'm actually going to put this next to it, y dash, so that you can remember. When somebody wants the primitive, that means they've given me the derivative. I'll go back to the original, and the original is make the index go up by 1, and whatever that number is, divide by the same number, and don't forget, plus C. Now I didn't just put equals because x to the 5 does not just equal this, they are not the same function, so I'm getting your brains to say, if this was the derivative, then I'll tell you what the original was. Here we go again. Add 1 to the index and divide by the same number, and don't forget the plus C. If you ever wanted to check if you were correct, you should be able to do a derivative on this and get back to that original. So if you've got time in the break and you want to make sure you are, applying the right rules, see if it works. What happens when it's an x on its own? What's the index that you know is there but can't see? We all know it's a 1, so that when this is y dash and it's going back to the original, it says add 1, divide by that number, and don't forget to add the constant. Now here's where it starts to hurt. It's got an x to the minus 2. All right, so then it says, can you remember, if this was the derivative going back, it says add 1. Now this is where it starts to hurt. Add 1 to a negative 2, and the answer is negative 1, and put the same number underneath. Now you might not think dividing by minus 1 will do much, but it will affect your signs because you are now dividing by a minus 1. If you had to rewrite this, by the way, because I need you to be able to go in and out of index form, so this one here written out of index form is also known as minus 1 on x. So why the minus at the front? Because I was dividing by minus 1. Why is it a 1 on x? Because an x to the minus 1 gives you the 1 over. And so you're going to need to know that because you're going to put a lot of this in to your calculator over and over and over again. And you don't really want to have to keep pushing in this index form. So learning how to manoeuvre around some simple things. Now this guy here seems to stump a lot of people. So people say, where's the x and what's its power? There is an x, a constant has an x to the 0. So what happens here is when you go backwards, it would say the 5 stays where it is, it's a constant, the x gets a 1 and it gets divided by a 1. So in fact, this guy, all constants, if the 5 was just on its own, it goes backwards to a 5x plus c. Does that agree with what you know about derivatives? If you do the derivative of this line here, the answer would be 5, just a constant, okay? So these are just pieces, okay? We've got to put all these pieces together. So it comes up as, if dy dx equaled 3x squared minus 8x, it says what was the original. So first thing is you put your 3, which is just a constant. Remember, these guys are constants. It's the x to the 2 that gets worked on. So it becomes x to the 3 over 3 minus the 8 is just a constant. It's this x to the 1 that's getting worked on. Becomes an x to the 2 divided by 2, and then I've got a plus c. Now I know what you're all going to say. Can I simplify that in my head as I go along? I know you will, even though I will say, in all my working, I still show every single piece. You know why? Because when I'm in a test, when I'm in a quiz, I get a little bit nervous and I probably make mistakes on really simple things. So it is still worth your while to write that out and then go back and simplify the 3's. They become a 1. Simplify the 8 and the 2, and then you've got your answer. Please don't think you have to get those answers straight away, because you will find the numbers get quite difficult, and then you're making your brain do a lot of hard work in its head up here rather than on this beautiful white piece of paper that we give you in our quizzes and our worksheets. So the next one that pops up says, if I tell you g dash of x is equal to 2 over x cubed, what was the original? This is not ready, so I want you to put a couple of exclamation marks and say, you're the one sitting, you're the one who's got to realise this is not ready to be treated. Why is it not ready? Because it's not written with the x to the power of n. It's got an x to the 3 in its denominator, but it's not ready in the x to the n format. So you can see that to the right on your page, it has then been rewritten. So this is up to you and your index laws. So we will have a lot of people who won't know what to do with that too. So if you're a person who's a little bit rusty on it, I suggest you write, this is 2 times 1 on x cubed, and that's why it becomes 2 times x to the minus 3. You are now ready to go, so I'll put a tick on it to say that's in the right form. So the 2's just a constant, so the 2 stayed. You add 1 to the minus 3. So I know it sounds simple, but we will make mistakes on that little spot there. Add 1, and whatever that number is, you put it on the bottom. Plus c, because there's always a constant. Now do the simplifying. So don't be in such a rush. Do the simplifying and just sort of say, I will save time somewhere else so that I can do that and show all my steps as I go along. Okay? Now there are 3 for us, and then we'll take our break. Okay? So here comes the first one. It's got square root of x. What do you remember? Before you go anywhere, this is a y dash, so I'll put a y dash next to it. Is it ready? No, it's not. It hasn't got an x to the power. What do you remember? X to the power of a half. Now I'm a lover of fractions, so I'm going to be writing in fractions. If you're a decimal lover, go for it, but you will find yourself in a small sort of problem, but I'll show you where. Now we're supposed to get that ready. It's done. Now when I go to find the original, I'm supposed to add 1. I know that 1 and a half is 1 and a half. I will write mine as a 3 on 2, and I will put a 3 on 2 on the bottom. You will say, why would you do that when you could put 1.5? Well, the people that put 1.5, when you simplify your answer, you can't see that a 1 over a 1.5 should simplify. Leaving things in fractions is easier because when this says x to the 3 on 2, which I'm going to leave for a moment, divided by a fraction. Dividing by a fraction always meant multiply by its reciprocal. So if you can see the 3 on 2 as an improper, then the very next thing you write is swap it over, put the 2 and the 3, swap them over. So instead of the 3 being on top and the 2 on the bottom, you've actually flipped it, and keep this guy on the top. This is one way of writing the answer. How else can you write the answer? Because this is correct. You'll get that right. When we've got to use this, so in the next half of the lecture, when I've got to use this, it might be more useful for us to write it as 2/3. Remember that the 2 on the bottom means it's the square root of x and then cube it. So why have I done that? Because when I go to use my substitutions in the second half, you are most welcome to leave it like that, but you'll probably have to push a lot more on your calculator. I'll use this, and I use a lot less calculator buttons. All right? So it's just a matter of being efficient for your exams and quizzes. Round 2. Is it ready? So put down y dash equals. Remember, a 1 on x to the power of 3 is not ready, even though you think, but it's got an x to the 3 on the bottom. It has to be written with the x in the numerator, and the power happens to be a -3. It is now ready, so I'm about to find what y is. It says add 1, so if I add 1, I get this number plus c. Whatever I show up there goes down the bottom. I can leave it like that, or for when I come to my substitution, this would also be the same as the 2 was always on the bottom. See the -2? It was always in the denominator. The x to the -2 ends up living down the bottom in the denominator. So this is also the correct answer. Why do I want to know that? Because it will be easier for you when you substitute, if you see it in that format. Okay? What were you going to ask, Cara?
If you don't do it that way, if you don't simplify it, will you mark it?
Not necessarily. So if this is asking you next week in the A3 quiz, if it says that, then this is correct, all right? It's about when you've got to put numbers in and saving time. That's why this gets easier to substitute numbers into than that one there. But it's up to you. Here is the last one. It says if I give you the derivative, so that's an x to the 2/3. So the power is ready. Can you add 1 to it? So up to you. I'm an improper fraction type of person. A 1 and a 2/3. I know it's 1 and 2/3. So I know that that will give me an x with a 5 on 3. Okay? So remember, a 2/3 plus a 1 is the same as a 2/3 plus a 3/3, which is a 5/3. That's what I've just done. And then I'm dividing by 5/3 plus c. Why do I like that? Because when you're dividing by 5/3, it means it gets flipped. The 3 lives on the top, the 5 on the bottom. You can write the x to the 5/3, or you can also give it as 3, 5. That's the cube root of x and to the power of 5 plus c. You can also write that the other way with indices is that guy there can also be written as the cube root of x to the 5. Now the difference is when I have a number and I've got to do a substitution and I want to do it efficiently, I find this one more efficient than this one here. Because if I have to put a number like 8 in, if you put 8 into this one, just take the cube root of 8, it's 2. 2 to the power of 5 is, use a couple of fingers and you'll get 2 2s are 4, 8, 16, 32, you'll get 32. If you do it this way, you'll get the same answer, but your job is to first of all take the 8 and put it to the power of 5. Now I have to go to my calculator to ask it 8 to the power of 5, get an answer, which is quite big, and the cube root of that answer, I bet you, is 32. So it's a much more efficient way of substituting if you do that than if you do that guy there. Okay? Now we're just going to have our break, because then we come back and we have to put lots of numbers in. All right, we're about to do lots of numbers. So we'll go for a 5-minute break at about the 5 past by that clock up there. 5 past. Well, it is because that 2's dropped. Oh, okay. So this one here is not really M and it's not M dash. That is M dash. So I do like your M dash up here. So we'll just cross them out for a second because these are one or the other. You put it to equal 0, you got 12. You checked the second derivative, which was -2, which has to give you a max. So what were the two numbers? The two numbers were 12, because that's what you've got for x. And the y value, you told yourself here that y would equal 24 minus the x value, which happens to be 12. So the two numbers happen to be 12 and 12. the two numbers that will give you a maximum product, right, is 12 and 12. That's the second. Well, you've got to
find it and then leave
you
it.
just got to find it because that's testing that this will give you the max. Because what you've actually done is two numbers that add to the 12 will give you 1 and 23. But the product is just a plain old 23.
Yeah.
You could pick 5 and 19. Well, that's awesome. Now, the good product is 45 with a 4. That's about 9. See how the product is getting bigger?
Yeah.
But what you've done using calculus, figure out that if you get 12 and 12, this will give you the biggest product. And that's what all this is done without you having to go through all the numbers.
Yeah.
So you've been like a machine, but rather than going through this churning of all the numbers, you've gone and used calculus, found a stationary point, proved it was a maximum by doing this. But you see, the maximum, it doesn't tell you what the maximum is, saying it will give you a max. That's the
So it doesn't actually, like, you don't actually put it in.
no, that's just you proving that it will give you a max.
Yeah.
Yeah, so that's all correct. The two numbers are 12 and 12.
Okay. Thank you.
Keep it up, and then work solutions are up on black.
Yeah.
Look, it's okay to do it there if it's just asking you for the primitive. Right? Just said primitive, that's what I do. I've been doing this because in a minute I'm going to have to put numbers. I'm going to have to substitute numbers in that X position. So it's much better if it's probably written like that for our next case. Yeah. Yeah. So if you want to just say, I'll do it from the very beginning, that's fine. But you will be okay. Yeah, in the primitive question I'm using, yeah. And, okay, before we can do that, one of our questions, okay, that we're leading to is, if you've got any of the questions at the moment, you need this to be multiplied out. Because you can't face this, because this is what would really be a product. There's a function of x, and there's a function of x. Now we don't have a thing called a product rule in this world, so we have to expand it. But then once we expand it, even the first guy would say 4 times the square root of x. We'll have to change the square root of x to the half. So there's a few steps to get through before you even do this adding one. If that's what you did over there,
No,
or you did somewhere else, so that's the path we're going to take. So that's examples like that are about to come up. Nice work, because that's what we want to check on. Okay, the number, look for the substitution in it at 0 and 4. And we're about to pick up now is us putting those numbers in. And that gets up. It's only small details, but they're really important because every little detail we want to get in. Yeah. Okay? Yeah. Okay, we'll take the x out first because x is common. X is common. That's going to make life easier. Now this one is the one very brave, aren't you? And I did make it to my group. And I said, when you go to factorize this, put it equal to 0, factorize and solve it. This will give you 0. But this is a quadratic. And I think that one may be alright. It's got to do with the secondary factor. So this one here is still safe, I think, because a 2 and a 1 will do right on that one. So I know what you mean. One of the first things we do is only the most simplest factorisation, which is just put on the backside. And it may make life easier. First, then factorise the other side as well. 2 and a 1. Get the right signs in the right place. They're going to multiply to get 2, so there's got to be a 2 and a 1, and then I'll put my 2 and a 1, I'll tell you why. I would have had my 2 and my 1 sitting there. I always put my numbers down. Because this is positive, that means it will be a +2 minus a minus. change them into formula?
No, just like the K value.
No, because what they're just saying is that you're going to start at 1 and then you'll go to 2 lots of that and 3 lots of that. So really, the way that when you read that, so when you go to first year maths, you might see a lot more discrimination, because what they're saying is, first of all, put the A value plus 1 lot of sigma x, then put 2 lots of sigma x, then put 3 lots of sigma x, and then you go up to whatever that top number is. That's what they're saying. Whereas this one says, start with the A value and 0 lot, and then we go 1 lot, 2 lot, 3 lot, and then it always gets to the level 1 less than, you know, it stops, because we never count this guy down here. So that's just formally how it's written. But no, they don't technically change it. But it's a nice way for someone to let you know. Justin James, is that right? Justin James and Justin James. Because I'm a computer, so it'll be over here. In green folder. I'm pretty sure. I do, because I put in the front bit. There it is. Because now I don't have such a big group. Because it's too big, I don't want to carry it around with me. But the small group. I haven't got Daniel Mitchell. Mitchell. Yeah, so, Justin, question again?
No.
I don't solve that. All right, are you ready to go? All right, second round. Here we go, second round. So, you've now got the idea of what to do, the method. Okay, you've got the idea of the method. Now comes the symbols. It means the same thing as before. So they just came up with this. Anti-differentiation, okay, is also called integration, and it's represented by that elongated S, okay? So it's actually the integral. We call that symbol the integral. So when I read it, I say the integral of, and I'll say whatever comes after it. So that there is the symbol you get used to. It means the same thing. Your job is to go backwards to the original function. And it just tells you the mathematician who first came up with it. It tells you that the dx is written at the end because it's denoting which variable the function is being integrated with respect to. Now be careful, because in the tutorial and the worksheet there will be dt's, there will be du's, there can be d anything, and that just means you're not talking in x's, but you've changed the letter. So if it's in dt's, you're talking in t's. If it's du, you're talking in u's. So it's a little detail, but keep an eye on it, all right? It then says that sometimes this primitive function refers to finding the original form of a differentiated function by using that anti-differentiation. That term indefinite integral, if you're ever looking it up on, on a website or something, it will go and tell you that the indefinite, the reason why it's got the indefinite, refers to the result of integrating a function. Note that the indefinite part of this question means you should have a plus c. So, there are many questions you will need the plus c, and you're going to find out in a moment when you don't need the plus c. So the plus c is there when you have an indefinite integral, and you know it's an indefinite integral, okay? If you do not see the numbers, there's little numbers on the integral sign. So if we are integrating between set limits, we would not have to put that plus c part in, is what it's telling you down there. So there's a slight technicality when you need the c and when you don't need the c. Down the bottom of page 33 is the actual form, I guess. That's the one you want to remind yourself. If you are not in an x to the power of n form, then it's your indice rule. So some of you might want to put some things down on your resource sheet, referring you to your indice laws that you used to know, you used to be good at. And then we're just going to put into action on the next page. All right, it says integrate, and then it's got 4 parts to this with respect to x. Now those 4 parts get dealt with on an individual basis. They are already, this has an x to the 3, an x to the 2, an x, and this guy here is a constant. If you need to put it in, put a little x to the 0 if you need it. If this is the first time you've done integration, you might want to see it there. So what ends up happening is the answers are already there, but I'll just do them as if I was doing it as I went along. The 4 stays. X goes up by 1, and then that power sits on the bottom. You've already got this written down. Minus 3 times x goes up by 1, and it goes on the bottom. Plus the 6, x goes up by 1, and it goes on the bottom. And the constant, minus 9, the x goes up by 1, so it becomes an x to the 1 over 1, and I get a plus c at the end. Remember, don't take too many shortcuts. I would always write that, because then I'll come back and do the simplifying. Get the x to the 4, get the x to the 3. This becomes a 3x squared, and then this is a minus x plus a c. So that's how you end up finding it. Round 2, in front of you, already done. It says, I'd like the integral. I'll say it again, this is an indefinite because you cannot see any limits. There are no numbers sitting on top or on the bottom of that integral sign. So it's the integral of 2 over the square root of x. This is not ready, so I'll put a couple of exclamation marks. Be prepared to stop yourself because you will get carried away. It is not going to be good enough to put 2 with the x and the half on the bottom. That is not going to be good enough. You need your x to be up the top in the numerator, so this definitely has to go to x to the minus a half. And what happens to a constant? Well, that 2 can sit in the front here, or because there is only one term to this indefinite integral, the 2 can sit out the front and can then be dealt with later on. So because it is a constant and it's only got one term, you can do that or that. You can use either one, okay? You can use either one. Now, when you go to do the next step, the 2 stays where it is. It becomes x, and I'm supposed to add 1 to the index, which is a half, dividing by a half plus c. Now, most people will write that down and get that correct, but it's what they do with that half that they're unsure of. So again, I'm going to spell it out. This would have been a 2, this gets a reciprocal, so it goes up the top, so it gets this. So I didn't really need that fraction line down there at all. So in fact, this is 4 times x to the half, so you can either write it as 4 times x to the half plus c, or you can write it as 4 times the square root of x plus c. All right? Now, it's that divided by a half that's going to hurt most people. So remember, write it down and then deal with it on the next step. All right, we've got 1 to do. It's got a 1 over x squared plus an x cubed. So obviously I'll put some exclamation marks on the top guy because he's not ready. So I have to be able to stop myself. This is an x to the minus 2 plus an x to the 3. By the way, they are unlike terms. You cannot add them. So anyone thinking of doing a merging now is going to do an illegal merge. You cannot add those 2 terms because they do not look the same. They're not like terms. So here it goes. The first time I put this in, it goes x, I'm adding 1, and I'm dividing by the same number. I'll deal with it later. I'm adding 1, and I'm dividing by the same number, and I've got my plus c. Now, the first time through, it's quite simple. Just add 1 and put the same number. Add 1 and put the same number. Now do the tidying up. Now the tidying up on this one, this is a negative number, and the x to the minus 1 is also known as 1 on x. This guy has nothing to tidy up, plus c, and that's our answer. So it's being able to stop yourself before you go and do something silly. I know what that means. Most people will see this x to the 2, and most people think they can just make that an x to the 3. It doesn't work that way, because you have to have your x to the power, all right? You cannot have a 1 on x squared. You cannot integrate that unless it's ready. So say to yourself, be ready, be able to stop yourself. Now we turn into this last part, which is us going into the fundamental theorem of calculus. Again, what this lets us do is actually find this area that we've been trying to do. At the beginning of the lecture, we came up with an approximation. We did the left sums and the right sums, and we saw that they vary, but the more rectangles you take, the better your estimation gets. Pretty time-consuming way to find an area. What you've now come up with, or what they came up with, was a great exact value. This is an exact value. This is not an approximation anymore. And it says the area enclosed by a curve, the x-axis and the lines x equals a and x equals b. They've got to really give you where the area starts and where the area finishes. They've got to say that it goes to the x-axis because, again, the area needs to stop. Because if you didn't say the x-axis, the area would just keep going and going and going and would never ever stop. So your area would be infinite because it just would never stop. So they have to say there's a stop to the area. And what you're staring at is a curved side. So this is where your calculus is able to say, I can find that exact area by putting this integration, this antiderivative, into motion. Now, you see that it's got f of x there, and suddenly they become capital Fs. Now, those capital Fs are just another way of saying to you that this capital F is the primitive function that you have found, and this capital F is the primitive function that you have found. And they're saying, now put the b value in and take away the a value. So we're about to do this motion, and what it's about to do is say, I know how to find that primitive. That's what we just practiced a while back. We've practiced that. Now I'm actually substituting the two limits in there, and it's always the top number first minus the answer to the bottom number. Now this is where it starts to add small details, but they get devious, all right? So this is what it says. This is just showing you a very simple one. This is the integral of the function x from 1 to 3. Do you know what the function x looks like? What does it look like if I said draw it? Any suggestions? Jaden's doing a straight line. He knows it's a straight line. It's got a gradient. Everyone think about the gradient. It's got a y-intercept. Think about the y-intercept because it's about to come up on the screen. So this is actually asking me for the area under a straight line, and it's going to show me this in a minute. I'll put it in the slide comes over here. Here is the straight line that Jaden's talking about from x equals 1, the lower value, to x equals 3, and it got stopped by the x-axis, otherwise it would go forever. Now, what it's actually done is, the first thing it does is it actually finds the primitive of x. Now remember, that's an x to the 1. So where did they get it? They added 1 to the index. They got x to the 2, put it over 2, and now they put it in square brackets. Now the square brackets mean something to us. It means you are about to put numbers here and here. In this case, it's a 1 and a 3. Because that's informing us that what is inside the square bracket is the capital F. Remember, capital F is the primitive. You have found the primitive, and there it is there. That's what's sitting in that bracket, in that square bracket. Now your job is to substitute the 3 wherever the x is. So the 3 goes and gets dropped in there, so you get 3 squared over 2. The minus is always between the two answers. So this is actually the f of b minus the f of a. In this case, it's the f, capital F, of 3 minus the capital F of 1. So it gets 9 on 2 minus 1 on 2, and the answer comes out to be a whole 4. On the side, the graphics is just showing you that if you had actually done this another way, since we know it's a straight line, since the area is actually a trapezium, guy, but what they've done here is take the area of the bigger triangle, take away the area of the smaller triangle, and that's how they've ended up with their area of 4. Now, that's how you find areas of any curve, but in this case it had a straight edge. So it could have been done another way. So we need to be able to say, putting this into action, you can see this example on page 35. So first thing, this is the formal way of writing it. It says, if you're finding a definite, notice the word says definite now. It's no longer indefinite because it will now come to you with limits. So once the limits are there, you don't need the plus C's anymore on your page, and you now know that. You will find the primitive, there it is there, and I'll put the word there so you know that the capital F means you have done a primitive, you have gone and found the original function. Once you find that original function, you'll be very careful to show me the substitutions. So here's what happens. The x squared goes to, and you've got it written down, but I'll go through it manually. This becomes an x to the 3 over 3, and I'm going to put the square brackets with the 1 and the 3. Now you can notice that the notes have got that, and then suddenly the 1/3 got pushed out. Why did the 1/3 get pushed out? It doesn't have to be, it can stay where it is. If you only have one term, and you have a constant. Last time I did this, the constant was 2. This time the constant is 1/3. You have a choice. You can either make the 1/3 come out so that the only thing you are substituting into is the x to the 3. This only works if you have one term. Or you could just have left it as it was so that this line says 1/3, and then in this square bracket it will say I've put the 3 in and got 3 cubed, minus I'm putting the 1 in and I'll get 1 cubed. Now you will get the answer 1/3 of 27 minus 1, which turns out to be 26 on 3, and we're lovers of improper fractions, so I'm going to say a 26 on 3 is just fine. You don't have to change that. I would rather a 26 on 3. What if you didn't take that 1/3 out? Nothing much changes, because when you put the 3 in, you get 3 cubed on 3 minus 1 cubed on 3, and you end up with your 26 on 3. It does not matter. Remember, taking that constant out is handy, but it only works if there's one term. So round 2 in your example, you've got a 3, the integral of 3. Think about what that looks like. What does the function 3 look like? I'll give you a hint. Y equals 3. Again, Jaden's good on his graphs. He's gone straight across this time. That means he's given me a horizontal line. Y equals 3 is a horizontal line, all back from last semester. So it's actually finding, if you think about it, it's probably just going to find the area of a rectangle if you drew this on the side. So what happens here is you've got this worked out. It says, in case, again, this is new to you, put the x to the 0. If this is the first time you've ever done calculus and you need that, when you go to do the square brackets, it's a 3 with an x to the 1 on 1. And I know that seems silly to do it, but I'm always checking on myself because even small details can make a difference. Now that's only got one term. The 3 can come out if you want it to, from 2 to 5. So it says 3, and the 5 gets substituted, end of that, minus the 2 gets substituted, end of that. You end up with 3 times 3, which is 9. And you find that that would have been, all right, the area of a rectangle if you had drawn that up. You get the exact same answer. You will be substituting 3 times 5 minus 3 times 2. You'll get 15 minus 6, still gives you 9, Jacqueline, and you can leave it there, all right? Later on, when we do some harder calculus, you'll see there's an advantage, but right now you'll probably go, I don't think there's much of an advantage. And it also keeps that idea at, right now you might only see one term. It's about when there's more than one term. That's the danger when people take a constant out. So you can just leave it there. Now what happens to this guy? It's got an x to the 3 on 2. This one's for you to fill in. It's a lecture example on page 35. Now it wants you to add 1. Now are you good at adding 1? If you're not sure, this is a 3 on 2 plus a 1. Just on the side of your paper. This is a 3 on 2 plus a 2 on 2. This should be giving me a 5 on 2, and I'm going to put the exact same number on the bottom from 1 to 4. Now I'm going to flip that around, so it becomes a 2 and the 5. My x to the 5 on 2. Now is a good time to say, oh, I see why I may want to change that. So this is what I would say, the 2, the 5. X to the 5 on 2. The 2 guy on the denominator tells you it's a square root of x. And once you've taken the square root of x, you want to put it to the power of 5. Now, you may not see the difference. You may go, look, I'm going to be on the calculator, so it doesn't make a difference what you do. The more you're on that calculator, the longer it takes people. Because I watch you in your quizzes, the people that are in my tute, and I can just see your time is just being sucked up by that calculator. Learn to live without it, because this is what you're being asked. You want to first of all put the square root of 4 in to the power of 5 minus, and then it says the square root of 1 to the power of 5. Now the square root of 4 is not that difficult. It's 2. 2 to the power of 5. 2 to the power of 5. What do you reckon, Jack? 32. And a square root of 1 is a 1. A 1 to the power of 5 is still a 1. And in fact, what you can do, and even though this is fractions, guys, you can see that I've got 2 32s, which are 64, so I'll put on the side. Take away 2 1s, which are 2. My answer is 62 on 5. I really don't have to simplify that. I don't have to do any magic to it. I'm going to be happy, and so will Dave, if we put 62 on 5 as our answer. Now, I haven't had to touch the calculator. It's not that difficult. You're in advanced. You're only getting asked the square root of certain numbers. We pick our numbers so that they work. We don't give you the square root of 5 very often. So we make it so that it all comes out. Even if it was the square root of 5, leave it as a surd anyway. So are you ready for the next round? Now, these are only coming to you one at a time. One at a time. So this is just small doses. Next round, it's got an integral from a half to 1 of x to the minus 2. This is ready, so I put into play the primitive. Add 1 and divide by the same number. This is going to be a half. Now I'm a lover of fractions, so I'm getting out of my decimal. I'm going to change my primitive in there because it says minus 1 on x, and then I still haven't done my substitution yet. I just wanted to put that in. All right, let's do the substitution. It says minus 1 on 1. Here comes the part that's going to hurt. This says minus what you're about to drop, and I know that what I'm about to drop has another minus 1 on a half. So we'll go through that again. Once you get to this point here, be very cautious. What's about to happen are very small details, but they can hurt. I put minus 1 on, and I put my x in. Then this is always what sits in the middle of the f of b minus the f of a, remember? But what was being placed there was another negative, and it was a 1 on, and I put my x value in. What does this give me? This is a minus 1 plus, and then a 1 on a half is actually a reciprocal question, so the answer in total is a 1. All right? Now, just in case, if you've had this question or thought, will it always be a positive number? That's a good question, because if, when I get to the end, I've got some time for some spare questions, I'm going to show you, because at the moment they all seem to be positive, and you would probably say that they're meant to be positive, aren't they? They're all areas. So I'm going to show you something in a little while at the end. Here's the next one. Is this prepared? This is not prepared, and who's going to say it? Only you. You're going to be in a quiz, And the only person who's put the brakes on is you. Once you see some extra brackets, this means that this has to be expanded. So there's a couple more coming your way. Although this looks like the end of the lecture, there's a couple of spare slides that we're going to put in the bottom of that page there. So what's going to stop? You're going to stop yourself because this is not ready. We've got two jobs. We've got to expand. So the first job is a 4 times the root of x minus a root of x times an x dx. Now or later, it's got to be dealt with. That square root of x can't live on my page, so I need that to be 0 to 4. This is a 4 with an x to the half, and this guy here is an x to the half being multiplied by an x to the 1. Now you see how I'm using dots? I'm sure you've picked that up in calculus. It's a lot easier than putting multiplication signs because you get mixed up between your multiplications and your x's. What's the index law? Remember, I still have not done any of the primitive work. I'm still prepping. You can prep on the side if you want to. So what should you get when a minus an x to the half times an x to the 1 gets put together? An x to the 3 on 2. Again, I'm an improper fraction person. So that's a half plus a 1 is a 1 and a half, but my brain thinks of it as a 3 on 2. We are now ready to put the primitive into action. So here come the square brackets. 4x, I have to add 1, so this goes to 3 on 2, and I put my 3 on 2 on the bottom. Minus, this has to go up by 1, 5 on 2, and I see a 5 on 2 appears straight away. And it's going between 0 and 4. Now remember, you are most welcome to put all that in on your calculator, because if you want to sort of make sure it all sits on your calculator, go for it. I'm about to do some simplifying, which is the first guy. This becomes 2/3 of the square root of x cubed. Now I've done that all in one. I've done 4 times, I've done the reciprocal of a 3 on 2, and while I was at it, I changed my x to the 3 on 2, so it's the square root of x being cubed. This guy turns into a 2 on 5 with a square root of x to the power of 5 from 0 to 4. Here we go. We're putting the 4 in first. Are you ready? This is an 8 on 3 times the square root of 4 cubed minus a 2 on 5 square root of 4 to the 5. That's me putting the 4 in. Now it says minus. Now I'm about to put some round brackets around there because there's more than one term coming. Now here's a bit where you need to learn very early on. You're about to substitute a 0. Just because you substitute a 0 does not always mean the value disappears. It's going to hurt you later when we do the exponentials and the trig if you have that in place in there. So make sure you say, I'm just going to do it. I know most of the time the 0 will disappear, but just in case it's not that time. So it's going to be an 8 on 3 times by the square root of 0, and I'll cube it, minus 2/5 square root of 0, and I'll put it to the 5. Okay, so keep in mind. I know you're saying, why would you bother? It's going to hurt later on if you've taken too many shortcuts. Now, in fact, all of this is 0, so I'm not going to worry about any of that. And if I was doing this, this is an 8 on 3 times by square root of 4 is 2. 2 cubed is 8 minus 2/5 square root of 4 is 2. 2 to the power of 5. You should have heard this number a few times. Now, you can do that on a calculator if you want to because it's merging two fractions. All right, one's on a denominator of 3, one's on a denominator of 5. So merge them both, bring them together. Let the calculator do the rest, so I let it do the last part. And check on me, please. Do you get the same answer? 128 on 15?
Yes.
Someone check 128 on 15, and I'm going to leave it as an improper. Okay, so you can convert it if you want to go one extra step. Now put a big highlighter around that and say, who's going to notice? So you have to notice those brackets that need expanding before you go anywhere, and you also have to notice a bit of indice laws. Now we're about to add a couple of extra examples. We'll still be out of here in plenty of time, So this one here has got an x to the 1.5. This is an indefinite. There are no limits. See, there's no numbers. So I have to remember that I will definitely get a plus c in my answer. So here I go. Add 1. So for the moment, okay, I'm adding 1. Again, I see that as a 3 on 2. So this is going to be, add 1, that's a 5 on 2, and I see the same number on the bottom. Plus an x, I see that as a minus 3 on 2. When you add 1 to a minus 3 on 2, or a minus 1.5, you get a minus a half, and you divide by the same number. Now remember, don't take those shortcuts, because all of those fractions are really going to irritate you, because you're going to get them wrong, and you'll say, I can't believe I'm letting those little fractions, okay, lose me marks. Fix this up, and when I say fix it, it means that will come out to be a 2 on 5. I would probably just leave this because I'm not doing any substituting, so I'm just going to leave it like this form. I'm dividing by a negative number, so it becomes a minus 2 on 1, which you don't need to show. And as I just said, because I'm not doing any substituting, it's sort of just a common thing that we leave it in that form, but you can go one more step. Now I had the plus c's. I'm making sure that the plus c was needed because it was an indefinite, so this guy here was needed. There's 2 more of these spare questions. What if the question comes to you like this? And again, this is not a time when you go, oh, I think this is a quotient, because that's going to creep into your head. You cannot use any rules. There are no rules except you need the actual term to be an x to the n. For me to do this question, it means I have to work on it first. So the x to the 3 has to be divided by the x squared, and so does the second term. Now again, who's going to halt you? Who's going to stop you from getting carried away? Because I know what people will try. They will try and use the rule on the top, and then they would try and use the rule on the bottom. It's not usable. You cannot use this rule, okay, in numerators and denominators. So the first guy gets simplified to an x. The second guy gets simplified, so it says minus 2 times an x to the minus 2. Now again, I haven't gone and done the primitive yet. I've just prepped it. So here I go. It's an indefinite, so it's definitely going to need a plus c. First guy goes up by 1, divided by the same number. Second guy goes up by 1, same number seen on the bottom. Now all of that comes out of me very quickly. I then go back and deal with any small details, like a minus 2 divided by a minus 1 is a positive 2. And again, you can leave this x to the minus 1, or you can put him back where he belongs, down the bottom. But because it's an indefinite, I'd say I'd leave it like that. So there was another alarm bell. Don't go too fast because you need to stop yourself. And there's one more, same sort of idea. And the same thing could go for whether I write, 2x plus 4 squared. Even that, people go, oh, is that a composite rule? Is that one of those functions of a function? Remember, you're thinking derivatives. This is integrating. This is the antiderivative. So you have to expand your brackets out. Okay? So that one there, very similar to the one we did before. When you expand it, this becomes the square root of x. The second one becomes just a positive 1. Now this is almost ready. This is a half. This guy is a constant. And then this is now ready to go. Remember, I do not go doing that primitive step. I don't go jumping until I know I'm ready. This is now ready, so add 1. So this is a 3 on 2. Show the same number. This is a constant. And that's going to hurt people because people will just slightly go, oh yeah, no, I think it's a 0 answer. Remember, this is not a derivative. This is actually going to come back to life as an x. It's an x on 1 on 1. And if you want to tidy that up, this gets spun. See how you will become lovers of fractions and you'll say, why couldn't I see that before? Now I think that's the last spare one Dave threw at us. All right, now those last 3, okay, were spares thrown in. And I was just mentioning that when you go to do your integrals, if you've got numbers here and here, and you get a negative answer, that is not wrong. So in the tutes and also in the worksheet, if at any point you get a negative, that is not wrong. We're going to link it next week when we talk about the areas. But a negative answer just means if you had drawn this particular shape, the area of the curve was probably under, okay, was probably under the x-axis. So it's still finding an area, but it's coming in negative. So don't panic if you get a negative answer. Now I hope everybody's good. Go look up the worksheets, get your head back into derivatives, max min word problems, go and attack that worksheet. Answers are up on Blackboard. And if there's anything else you need to know or check, please come along. We've got drop-ins. And Lincoln, I think, is it, coming to my Thursday tute? Come Wednesday as well, Lincoln. And if anyone wants to ask anything, come along. Farewell. See you guys. See you, Joan. See you, Orawan.
So, Friday.
Yeah, what about Friday?
Are there any other shoots on Friday?
No, we only have 2 tutes because the group got smaller. Because the group...
They're only at 9 a.m.
they're both at 9, yeah, they both are.
What's the worst possible
Well, hang on,
time
you
ever?
walked in at 1 o'clock and said that wasn't a good time. You're coming in now saying 9's not good. When do you think's the optimal? What's
There
the
is
what,
no optimal
what
time
is the
for
optimal maths time, Asha?
All the time.
All the time, I'm with him. I do maths in the morning until the night time.
I think in the afternoon, after a good feed.
Well, have a good breakfast. Where are you coming in from, Lincoln? Are you coming in from far?
Says
So what are you coming in, driving or...?
no bus. I catch a bus at 6:45 in the morning.
And what time's it getting?
7:45.
And how many days are so the one that comes after that, or there isn't one?
There's an 8:45,
Coming in.
and that comes in at 9:45. So that's like me arriving 15 minutes
So
late.
you either have a 6:45
Yeah.
or
the
the
8:45.
8:45 start.
Yeah.
Okay. And how many days do you come in?
But
You have to come in 5. Well, we want to see Dave about that.
actually, it's okay.
It's okay.
It would have been fine if I didn't pick camp. Only runs on Tuesdays and Thursdays. Sucks.
Okay. But that should help your maths then. If you put your maths tube in the morning, does that
All
work?
that.
Yeah, I know, but I mean, so therefore, like, does that not help you? What do you have to come in on Friday? Bring your maths to Thursday morning. Do you still have to come in on Friday or something?
Yeah, gym basically. That's the only reason I picked it to go on Fridays is so that I'd come in for the gym.
Oh, the gym.
Yeah.
Okay, all right, fair enough. You need that too. All right.
Yes, of course. The only important thing in life, gym and math.
Well, yeah, they're both at 9. That didn't save you a day, so yeah, whichever one you want. You know.
Yeah, Thursday's probably just going to be enough to just come in for the entire day. I suppose I could dedicate Friday to a study
You
day.
could do that. You could. And a bit of gym. Do a bit of both. You know, study rooms over there, like, you know.
I've not been over there.
I know.
I don't think.
See, on one of those days, I'll keep an eye out for you.
time. Not that far.
Maybe you start trying to model the balances.
They use telescopes to shoot photo receipt, and then they use